not have a dimension, very small. Buckyballs was an example. Then 1D was carbon nanotubes. That was an example of 1D things that would be very long but very small diameter. If you unroll a carbon nanotube, we find graphene. Graphene is a 2D material, very thin and very flat, right? It's the thinnest ever material known to human being. Now, there is, if you think about it, we make things so small, we reach the atomic limits. When we reach atomic limits, we are basically messing up the normal atomic structure. I shouldn't call it normal, but I would say, okay, the atomic structure that we know it at a larger scale, right? We know stuff, material, which is composed of many, many, many layers of atoms. But when you get to single atomic layer or a few atoms together, we are basically interfering with the atomic structure or atomic level energies. That's the idea what you say quantum confinement. So we'll look at today on the what is quantum confinement and why does it matter. You must have studied Bohr's atomic model maybe in high school, right? So Bohr's atomic model, these kind of theories were basically we last century when we could do experiments where we were looking at atomic level things or subatomic particles or electrons. There were scientists who realized that you cannot use large scale theory or large scale equations to understand physical phenomena or electronic phenomena at atomic level. So those of you who have taken or are taking solid state devices, we have discussed this there, that then they had to come up with equations or rules which can explain atomic or subatomic scale properties. And that's what you call quantum mechanics, right? We hear the word quantum mechanics. So quantum mechanics is those set of equations or rules that we have modified from large scale observations, but now we do certain approximations or we have certain kind of rules, new rules for that small scale. So we call that quantum mechanics. So using it from there, now since we are dealing with those atomic or subatomic particles, we call this situation quantum confinement. And there are a few things which in all semiconductor materials we call it band gap. So there is valence band, there is conduction band. And again, this is from high school chemistry. We talk about valence band. I'm going to draw it here. We say, okay, we make conduction band at the top and we make valence band at the bottom. And we say that electrons at 0 degree Kelvin, all electrons are here in valence band. But then we apply some voltage or maybe heat or maybe light. But the idea is we give energy from outside. So electron jumps across the band gap. So this is called band gap forbidden zone where electrons cannot stay there, but they have to jump and they have to go up in the conduction band before they will be available for conductivity. And when they do that, they leave behind holes. Now, this is the structure of what we call as energy band. When you make things small, we start messing with the band gap. When we do that, we confine electrons in smaller dimensions. Instead of 3D, where they can go everywhere, if you make it too thin, like it is shown here, 2D quantum well, now they are confined only in 2 dimensions. They cannot go up or down. But if you make it into wire, a very thin wire like carbon nanotubes, now we call it 1D, one-dimensional quantum wire. So now electrons can go only in one direction, ahead or back. If you make it for even further smaller, we call them 0 dimensional, which is where here it says quantum dot. We'll talk about quantum dot, but think of quantum dot like a particle, small nanoparticle. Now, this phenomena of quantum confinement, again, quantum confinement is when you make things so small that we start interfering with their physical structure and their energy structure. We call it to be quantum confinement, and it becomes apparent below 2 nanometers. Now, when this happens, basic concept is we are now confining electrons or confining electronic properties in those small dimensions. Okay, now what are electronic properties? Electronic properties, for example, diodes. What is the how much voltage we have to apply before a diode becomes active? Electronics. You guys have done electronics, right? What is the how much voltage we have to apply before like a diode becomes active?
Point 0.7 volts.
Oh, exactly. Cecilia said right, zero point 0.7 volt, right? So zero point 0.7 volt is before that there's we call it voltage gap. So you are providing enough voltage to have enough electrons jump into to go to conduction band before they start moving and it start conducting. So now if you make it too small, we would be changing the band gap. When we change the band gap, the the device may become active before 0.7 volt. It may start on at 0.2 volt because you have made it too small, you have changed the energy. We may be adjusting the electronic properties by physical size. That's the idea of what you call quantum confinement. Now, when we talk about band gaps, we have to know a little bit about electron energies or hole energies because that is uh, more holistic way of looking at okay what energy or what is the level of energy. We'll not go there. We'll just look at the phenomena and look at where we can apply this in bio nano, which is ultimately where we are going in the next module as well. So again from the previous one, in a 3D, they all carriers. When you say carriers, we mean electrons and holes both. They can go everywhere. In a 2D, they can only go in a plane. In a 1D, they can only go in one direction as a wire. Now, when these things, the electrons or holes, the charge carriers, get confined into smaller dimensions, the states or the available positions are also confined. Now, we don't talk about available positions when we talk about conductors, metals, because in those cases, there are plenty of electrons which can, as you turn on the voltage, they can start flowing. They don't care about if there is empty space next to it or not. But semiconductor materials, they are crystalline materials. It's a very well-defined structure. An electron cannot go and move and start making current unless there is an empty site available, a hole available, right? So it has to jump, and if they many of them start jumping, we start getting current, zero point 0.7 volts kind of thing. In quantum confinement, we reduce the available energy states also where those charge carriers can jump. So essentially, there's a little bit more probability and those things involved, but the idea is that in semiconductor materials, it's not only the number of charge carriers, it's also the available energy states which are important for conductivity. Unlike metals, where you don't care about locations, you just start pumping and they start moving. Now, this is a little bit more on I've been talking about the band gap, right? So they are in valence band, they have to jump and go into conduction band. So I leave it here as text. So if you look at the recording, you can pause here and you can read through. But essentially, it's the same thing, which I just stated in on previous slides. That there is conduction band, there's valence band, and there is forbidden zone. For electrons to be available for current, they have to jump from valence band to go to conduction band. When they do that, they leave behind a hole. Electron goes in one direction, holes go in another direction. And when there is movement of charge, what do we call that? When charge is moving through a material, what do we call that? Is Amara with us?
Current.
Current. All right, fantastic. So that's current. That's what our ultimate goal is, right? So here it's a little bit more graphically. So we have electrons filled up in valence band, you provide energy, they jump, they go to conduction band, and hence they start moving. Now, when you say we do quantum confinement, if it's a zero dimensional material, if it's a crystalline nanoparticle, very small crystalline, the condition here is crystalline. Crystalline material is where they have long range order, right? We have seen those before. If you make a nanoparticle of a crystalline material, it would look like this. It's a cartoon, but it's a gallium arsenide cartoon. We call it quantum dot. When you say quantum dot, that would be a nanoparticle which can give out light. So here's the keyword. Okay, there are electronic materials, they would be doing conductivity. But one more thing they do is they have optical properties. And optical mean they can give out light or they can absorb light. Now, we all have optical devices on our cell phones, right? The flashlight or the camera. Flashlight gives out light, camera absorbs light. Quantum dots are these particles become too small, and now we can, they would give out specific wavelength when they are excited. But by changing their size, we can change the wavelength. That's an, let me repeat that, it's a very important property. And why it's important? Because one material in nature is has a very specific band gap. It can give only one kind of wavelength, one light color. It cannot give another light color unless you do quantum confinement. You make them too small. You go into nanotechnology zone. Now, by changing the size, we can change the wavelength that comes out of it. That's crazy. We are not changing the material property. We are not changing material in it, because at larger scale, if you want to change, maybe you want to, from red, you want to get another green light from a diode, you have to change the material itself from one semiconductor to other. Here, you don't have to change the material, you just make them smaller and smaller. When you make them smaller, they give out different wavelengths. And that's the beauty of quantum dots. That's what is special of about quantum dots. That's why we are crazy about quantum dots in solid state devices or bio nano applications. All right, they are semiconductor material. They behave same like metals. They, we can call them metallic quantum dots as well. But generally, they are made up of 2, 6, 3, 4, or 4, 6 materials. They, now this last line is important. They are band gap tunable by size, which means that by changing their size, we can change their optical properties. Hence, we can get different wavelengths out of them. Now, these are nanocrystals, and the cartoon shows that there's a band gap, right? And band gap is constant for every material or every material combination. But by changing the size, we can adjust the band gap. You have to remember this, bigger the band gap, smaller the wavelength. What we see that here. Band gap bigger, same material. It's the same material, but if you have made the band gap larger, okay, what's happening here? There are two, three fundamental concepts that are going here. When this electron jumps from here, the difference of energy goes out as photon, what we are showing here. The difference of energy is what changes into a photon. Now, when we have changed the band gap, we have changed the energy that would be coming out, and hence this wavelength. It's showing blue in that wavelength. We're not putting exact numbers there, but we'll get to the exact numbers also soon. Now, if you make that quantum dot larger, we make the band gap smaller. Okay. We make quantum dot smaller and smaller, the band gap becomes bigger and bigger. You see that from this figure? And that means energy is higher, frequency is higher, and frequency higher is opposite to wavelength. All right, you guys know lambda is wavelength and f, or we write v also. Different places there are different things. Are you with me with this relationship? Trust me, I can ask. Oh, there'll be a question on this. I always ask question about quantum dots because there are three basic fundamental relationships. We make them smaller, band gaps becomes bigger. Band gaps becomes bigger, there's more energy that's coming out of bigger band gap, right? Because the jump is bigger here. This jump is bigger than this jump, for example. Now, bigger energy means bigger frequency. Bigger frequency means smaller wavelength. With me, Cecilia? Rachel, Orlando, Hector, Luis, I can't see Amara. All right. Now, what's the big deal? That's the important thing is if one system, a biological system, if that's biocompatible with one of these or any other material, right? We can use the same material, different sizes, and we can get multiple lights from that tissue. One light, maybe we coat specific size with specific antibodies, so they bind to only cancer. Another antibody that binds to another cancer. Another antibody, same material, but now the coating is making them go to very specific tissue. When you scan the animal, we can see exactly which one is staying there, which one is gone out, right? From that wavelengths, we can know what kind of disease is there in that living system. I'm not saying human, but of course it's applicable to human. Now, quantum dots have been evolved over a long time. They used to know them in 60s. They were companies that came up, but they were expensive to make and they were not stable because after some time they would stop giving out lights. So there's now this Los Alamos. I met this lady who works on these quantum dots at LANL. They came up with quantum dots that give 3 electrons per photon. Now, why we are talking about photons? Because for this electron to go up to start with, it has to, this electron has been made to jump from conduction band to go here to start with. And then when it comes back, it gives out this voltage or this light out of it, right? You have to excite it first. So they came up with a scheme where you could use one photon and get 3 electrons out of it. Sorry, I pushed the wrong button. Let me. And we use quantum dots for biological tagging. Now, this is when you come together as teams. I looked this up. This is a fascinating direction because nanotechnology, a major direction of nanotechnology application in biology is looking inside the body from outside without opening a system, without opening, and I say system, I mean body of an animal. So they have done biological assays where they are looking for specific molecules like maybe we all know simple molecules like insulin, sugar, we know cholesterol, right? There are lots of molecules which you want to know how they are inside. We want to look for maybe DNA, disease DNA. We want to look for biomarkers related to cancer, Alzheimer's, ALS. So there are specific molecules that our body starts making more or less, which indicates there is a disease. So they have done that to tag those uh, chips to see. assays and to microarrays. They are
So,
used, yeah,
Dr. Iqbal, I don't know if you remember about my research. Well, the research paper I read for the KPR, that it
right,
was the microchip device that it would like level the cancer cells.
right.
So is this like the method they use? Like, could be this one, like to tag and to level? Because I think that's the only part I didn't get like 100% for sure, like
So
how they did to level the cells.
I don't know exactly that paper, but it's very common where they use quantum dots. So you have to remember quantum dots are nanoparticles, it has optical properties, and they are crystalline nanoparticles. They excited with certain wavelengths, they give out certain wavelengths, and the wavelength that they give out can be adjusted based on the size. It might have been that. So
Thank
the
you.
applications labeling of cells is very common, not just cells, but the intercellular between the cells or inside the cell as well. They used to, so we do them for in vivo or in vitro, maybe in the petri dish or in the living system itself. They're used to look for pathogen and toxins as well. Pathogen, living things that infect. Toxins, toxic materials that may go and result systems to break down. So they are these applications that have been used. Why do we do that? They are good fluorophores. Fluorophore or fluorescence is the emission of light, which happens when it absorbs a photon, right? And absorb when you absorb a photon, basically you are providing energy to those electrons to jump from valence band to conduction band. You switch off absorption or you keep it on, then the electron comes down, it gives out another wavelength, and that's wavelength that we are looking for. So they quantum dots can absorb broad range of wavelengths, but they give out very specific wavelengths, very narrow range of wavelengths. That's why we like them, because you can use white light, which has bunch of wavelengths, but what it gives out is only very fine specific wavelengths. So we can exactly know which quantum dot is emitting in a system. So here's an example where they used a broad absorption and they injected the mouse with quantum dots of different colors for different medical targets. So they were looking, so each quantum dot is coated for specific molecule or specific tissue that it's supposed to bind. And you put it in the microscope, you shine the light, and you see very specific light coming from those particles. So now you have to understand these are particles which would accumulate there. And when there are a bunch of them get together, and then the light is high enough for us to look at outside. Now, this is another very interesting plot. And what it does is you have to understand what is happening on y-axis. We are changing the diameter of a quantum dot. What kind of material are we using? Okay, let's look at first cadmium sulfide. So there's one material, one combination of material of two elements. But the beauty is, it's supposed to, at large scale, it's supposed to give only one wavelength. But when you change the size, for example, you go from what is 5.5 to go to here, slightly below 3, you see it can undergo dramatic change in wavelength. So from 420 to maybe it goes to 475. Now, let me make sure everybody knows what does a wavelength mean. A wavelength of light. What? How does it look? It comes out as a specific color, right? So wavelength means a specific color. So if you make the size change, you can see different wavelengths from the same material. This is a fantastic example. Another one. This is much more profound. And this is indium arsenide quantum dots. Your size is changing on x-axis. What's the size? Probably about 3.25 and goes to 6 nanometer. And it is a dramatic change in the wavelengths or the color of light that it would give. it's I'm very excited to see, or I don't know if you can see or understand what I'm talking about here. The small change in size can dramatically change the wavelength that you can get from the same material quantum dots. And that's why it's used so much, because you can use one material and get different kind of wavelengths from that. So there's a whole bunch of materials that are shown and their diameters and the wavelengths that you get out of them. They're used for optical storage devices as well, right? Now, this is an example why we the Blu-ray technology became available. Now with Blu-ray, you can write much more data because the laser is very sharp in there. So you can high definition movies or materials or whatever media there on Blu-ray. If you compare that with what was the technology before Blu-ray?
Well, it was just DVD, but there was a time where it was HD DVD that was competing with
HD
Blu-ray.
DVD, right? So they were trying to use different densities. So from DVD 4.7 GB, how many GBs we can put on a Blu-ray disc? It's about 10 times. It's about 50 GB, I think. I have some numbers somewhere. Now, there's another application in energy, especially solar cell. Solar cells, the idea in solar cell is when you have the light that strikes a solar cell, when light strikes the semiconductor solar cell, it makes an electron go from valence band to conduction band. So we have a hole formed at the back. So this pair of electron and hole is called exciton. So exciton, they recombine very quickly. And that's what we do in solar cell. We want to sweep them out into circuit before they recombine. So with quantum dots, we have got some phenomenal things where we can create more electron hole pairs from one photon. So which means you'll have higher efficiency. And you can create from one electron, it can strike another electron, it can cause number of electrons to come out instead of just electron hole pair. So that's another thing what it has done for the energy generation as well. So is the similar thing that we have talked before, just wrapping it up, that you go from bigger size to smaller size, band gap goes up, means energy goes up, means frequency goes up, which means wavelength goes down, right? So all these things are interconnected. And we then look for specific wavelengths from that material coming out. There are, and making quantum dots is not super difficult. There are videos online which show you, but you have to have specific chemicals to starting chemicals. You need to have special, very controlled temperature to do this. You have to have some certain gases to keep up and maintain a temperature in there. Now, yeah, this is the comparison on DVDs and Blu-ray. So it has gone from 4.7 GB, which was a DVD, to 45 GB now for the Blu-ray disc. And wavelengths, this is a simple relationship between wavelengths. Going from, say, if you say 500, if you go to 600, you see from this bluish green, the wavelength changes to orange. And so these are very small variations of colors that you can see from changing the wavelength of light. All right, so the light emitting diodes is another example. The LEDs that we use are just diodes, but if you get the quantum confinement in there, we get very different, many different varieties of colors and different intensities, high intensities of light. But of course, they'll become expensive. So we call them QLEDs. They are better in tuning specific wavelengths, so very specific light, and they are better in efficiency as well.